Hello, thanks for watching our videos for probability and statistics. In this video, we will talk about gamma and exponential distribution. Gamma distribution and exponential distribution are related because exponential distribution is a special case of the gamma distribution. And both distributions find a large number of applications and play an important role in both Queuing theory and reliability problems. Time between arrivals at the service facilities and time to failure of component parts and electrical systems often are nicely modeled by the exponential distribution. So exponential distribution and gamma distribution model the random variable, positive random variable, which often be used as the time between events. The gamma distribution derives its name from the well-known gamma function. So first we'll see this is the gamma function. So gamma alpha is the integral of x alpha minus 1 in power times e minus x in power. Then this projection term take integration of dx from 0 to positive infinity. And alpha is a positive number. And the gamma function has some properties. For example, gamma n, if n is a positive integer number, gamma n equals n minus 1 times n minus 2 and so on, and times until gamma 1. And the gamma 1 actually is 1. So gamma n equals n minus 1 factorial. Here is equal, not minus, equal. And gamma 0.5 equals the square root of pi. So gamma function is very interesting. So the gamma distribution has its density function. So gamma distribution has density function of x alpha beta, where x a random variable, gamma random variable, alpha beta parameter equals 1 divided by the beta alpha in power, then gamma alpha. This is gamma function, right? Then times x alpha minus 1 in power times e minus x divided by beta in power. Both alpha and beta are positive numbers. And the mean and the variance of the gamma distribution. So mean is alpha times beta, and the variance is alpha times beta squared. So these are several gamma distribution density function. So this density curve, for example, alpha 1, beta 1, alpha 2, beta 1, and alpha 4, beta 1. So you can see where alpha becomes larger and the density curve becomes more symmetric. And now we look at exponential distribution. So exponential distribution has its density function is fx beta. So this beta is actually same as the parameter in gamma. So equals 1 of beta, then e minus x divided by beta in power. So you can see exponential distribution actually is a special case of gamma distribution where alpha equals 1, right? And the mean of exponential distribution is beta and variance is beta squared. So alpha is 1 here from gamma distribution. And exponential distribution and gamma distribution are both related to so-called Poisson process. So we know Poisson distribution is used to compute the probability of specific numbers of events during a particular period of time or space or span of a space. So exponential random variable describes the time required for the first event to occur. So this is actually two distribution model the same problem, right? But for the Poisson distribution, this actually model how many events occur during a specified time period. But exponential distribution model the time until next event occur. So this event is actually the same. They are Poisson process. So for example, using the Poisson distribution, we find that the probability of no events occur in the span up to time t is p0 lambda t. So this is the mean in Poisson distribution, and 0 means until time t there is, so before time t there is no event occur. So until time t the first event occur, and so which means in the time t there is no event occur, right? So this probability is e minus lambda t. Actually, this probability is same as the probability the length of time until the first event will exceed s. X is the same as the probability that no point events occur until time x, right? So in Poisson process, Poisson distribution, so between time event x, there is no event occur. And for exponential distribution, until there is no event occur until the time of x. So this is actually the same thing, right? So that's why exponential distribution, the probability of px larger than x equals e minus lambda x. So these two has the same form, right? And in exponential distribution, the cumulative distribution of the function for x, that is 1 minus e minus lambda x. From the previous page, the probability of x between 0 and x, which means there is event occur before time equals x. So this is the probability of event occur within the time interval of x. So this probability is 1 minus e minus lambda x. So when we differentiate the cumulative distribution function above to obtain the density function, so exponential distribution has density equals lambda e minus lambda x. So which is the density function of the exponential distribution with lambda equals 1 of beta. So beta is the average time between events in a Poisson process, beta, right? An exponential distribution in reliability and a component of machine lifetime problems are influenced by the memoryless or lack of memory property. So what this means? So this means the probability of x larger than t0 plus t given x has elapsed t0. So this means the probability of the event not occur in the next interval t given it has not occurred t0 time. Though this is same as the probability of x larger than t. So the condition of x larger than t0 has no effect of the next t event, t time interval. Though there is no punishment through wear that may have ensured for lasting the first t0 hours. Thus, the exponential distribution is more appropriate when the memoryless property is justified But if the failure of the component is a result of gradual or slow wear, as in mechanical wear, then exponential distribution does not apply, and either the gamma or the variable distribution may be more appropriate. So exponential distribution is a very ideal distribution, because you have, for example, have a light bulb. It has been used 1 year, but no problem. So if we assume this is this product follows exponential distribution, that will come next year. If next year, no problem, the probability of next year, no problem, same as it is a new one of using 1 year, no problem. So it has used 1 year. But the probability of the second year, no problem, is same as if you buy a new one using 1 year, no problem. So this is ideal for the exponential distribution. But if this kind of things is not justified, you cannot use exponential distribution. You have to use other distribution like gamma. So gamma with alpha not equals 1, and another distribution called a variable distribution, which we will talk about later. And whereas the exponential distribution describes the time until the occurrence of Poisson events, or the time between Poisson events, the time occurring until a specified number of Poisson events occur is a random variable whose density function is described by the gamma distribution. Though this specific number of events is the parameter alpha in the gamma density function. Thus, it becomes easy to understand that when alpha equals 1, the special case of the exponential distribution occurs. So what does this mean? So in gamma distribution, we have two parameters, alpha and beta. We have talked beta is mean time between events, because both gamma distribution, exponential distribution, they are just come from the Poisson process. Poisson process is the event occur during a specified time period with a lambda with the average occurring rate. So if we want to model the time interval until the next event, so this is an exponential distribution because alpha is 1. So in a gamma distribution, if alpha is 1, alpha models a specified number of Poisson events. So if we only model one number of Poisson events occur until one time occur of the events, so this random variable time interval is exponential distributed. But if we want to, for example, want to know the random variable of time until next 3 events occur. So in this case, alpha equals 3. So this is gamma distribution, not exponential distribution, because exponential distribution only for the random variable time t until next one time event occur, right? So next we will take a look at an example. Suppose that a system contains a certain type of component whose time in years to failure is given by t. So here the failure is like event, right? And the random variable t is modeled nicely by the exponential distribution with the mean time to failure beta. So beta is the mean time, average mean time between failure, right? Beta is 5. If 5 of these components are installed in different systems, what is the probability that at least 2 are still functioning at the end of 8 years? So the solution is first, the probability that a given component is still functioning after 8 years is given by, so if we only, first we will focus on only one component first. So for this one component, the probability of t larger than 8, because this follows exponential distribution. So the probability of larger than 8 equals this form we have shown in previous pages, right? E E minus x divided by beta, right? So this probability is about 0.2, which means for one component, it can be used larger than 8 hours is 0.2, this probability. Then next, let x represent the number of components functioning after 8 years. So this is a binomial distribution. So we want to know how many. Here is x larger than 2, right? Larger than 2 from 5, right? So this is a binomial. So here we can use a binomial distribution with n equals 5, x equals and larger than 2. So it's cumulative, and with an average success rate 0.2 in the binomial distribution. So we just summation from x2 equals to 5, and with the success rate 0.2 for this binomial, so the result is about 0.2627. So this means 5 of these components are installed in different systems. The probability that at least 2 are still functioning at the end of 8 years. So this is the probability at least 2 functioning after 8 years, right? So example 2, we will use gamma distribution. And the problem is, suppose that telephone calls arriving at a particular switchboard follow a Poisson process with an average of 5 calls coming per minute. What is the probability that up to a minute will elapse by the time 2 calls have come to the switchboard? So the solution is, this is the Poisson process, right? And with time until 2 Poisson events, this will follow a gamma distribution, right? Because here this alpha equals 2 with a gamma distribution with beta equals 1 of 5. Because average 1 minute have 5 calls, so the average time between events is 1 of 5, right? And alpha equals 2. So that's easy. We denote by x the time in minutes that transpires before 2 calls come. The required probability is given by the probability of x less than 1, less than equal to 1, because this is 1 minute, right? So we want to, here we want to focus on 2 calls come. But in minute, 1 minute until 1 minute, right? So within 1 minute, so we want to know the probability of this random variable time, which follows a gamma distribution, right? We want to know the probability of this random time less than 1 minute for the 2 calls come, right? So it may come 2 calls at the end of half a minute. This is also correct. So we will just want to know within 1 minute there are 2 calls come. So this is the probability of x less than 1 with a gamma distributions density. Then we take integral from 0 to 1, right? So the result is about 0.96. So it's a very highly likely, highly probable that within 1 minute there comes 2 calls. Because average 1 minute has 5 calls come, so this is quite high probability when the 2 calls have come within 1 minute, right? Thanks for watching.